Assalamualaikum warahmatullahi wabarakatuh and a very good morning. My name is Muhammad Hakim Bin Nasaruddin and my metric number is 192363, and today I will be presenting my final year project, and the title for my final year project is Mechanical Design and Finite Element Analysis of Lunar Rover Implemented with Flexible Metal Wheel, and I am a student under supervision of Dr. Adi Azrif bin Basri. So my presentation for today will be divided into 5 sections. For the first section is introduction, literature review and gap, methodology, result and discussion, and also conclusion. So firstly, let's take a look at introduction. First is project background. Okay, exploring outer space has become a globally important task according to Yang et al. And according to Yuan et al., the utilization of autonomous rover has been proven to be a successful method, but these rovers are expected to perform an increasing number of high-risk and difficult tasks in harsh environments. For example, thick layer of lunar, soil powder, and the gravity of the lunar is 1/6 of the Earth's gravity. And then the complex terrain of the lunar rover, like rocks, craters, and also random slopes. According to Yang also, the rover should possess an excellent traction performance and the capability to traverse over any obstacles. A flexible metal wheel can be an excellent alternative, according to Zhu et al. Then we will take a look at the problem statement. Okay, a manned or unmanned lunar rover is typically loaded by a payload and travels over complex terrains. And conventional wheels, such as rigid wheel and pneumatic wheel, often impose a substantial amount of stress and strain to the critical components of rover. These include metal motor casing, drive shaft, and also the frame. Then, what is the aim and objective for this project? So the aim of this project is to investigate the performance of the lunar rover implemented with conventional wheels. And the second one is we want to investigate the performance of lunar rover implemented with flexible metal wheels. And there are 3 objectives for this project. The first one is to conduct finite element analysis simulation of the flexible metal wheel design and validate with the simulation data from Zhu et al. And then the second objective is to perform static load simulation for both models, the lunar rover with conventional wheel and the lunar rover with flexible metal wheel. And the third objective is to compare the mechanical properties and where is the location of concentrated stress and strain distribution between these models. Then these are the literature review. Okay, this is the reference that I use and recent studies on the analysis of wheel of the rover from the until 2016. And as you can see, the literature gap for my FYP project is the research on the comparison of performance between lunar rover implemented with conventional wheel and lunar rover implemented with a flexible metal wheel with single rim and twinkle classes using finite element analysis is very limited. So as you can see, based on the bar charts below, the number of literature findings according to the parts of the rover, the wheel overcomes all of the major parts of the rover instead of chassis or frame, suspension, bearing, and others. So next we will take a look at the methodology. So these are the summary of finite element method. Okay, as you can see, there are 2 colors in the boxes. Okay, the first color is green and the second color is blue. The first color is the responsibility of engineer. Okay, while the second box, where the second color is the responsibility of the software itself. So as you can see, the summary of finite element method, firstly is we define the problem. Okay, we define the materials, the loops, the boundary conditions, and then we perform discretization or meshing process, and then we define element stiffness matrix or variational method. And then the software will perform a sample of the global stiffness matrix, and then the software will solve. After that, we perform post-processing and validation. So firstly is design and development process. There are 3 models were designed, and these include conventional wheel, flexible metal wheel, and lunar rover. These models were designed by using a CATIA V5R21. Okay, so we take a look at the major components of conventional wheel. Okay, there are rim, also a layer that covers up the rim. And then we take a look at the second second model, which is flexible metal wheel. And these wheels are composed of twin carcasses with 36 spring steel sheets on each carcass, a connecting ring, and also a rim. And then we take a look at the lunar rover. And the major components of lunar rover include rim, frame, drive shaft, and solid motor casing, also base. And then these are the setup that I use for finite element analysis software. Firstly is the material definition. So based on the models that I showed you earlier, okay, as you can see for lunar rover, all of the major components, the materials assignment that I use is aluminum alloy. And then for the conventional wheel, the rim I use aluminum alloy, while the wheel back is custom material. For flexible metal wheel, the rim I use aluminum alloy, while the twin carcasses and connecting ring I use custom material. So based on the left table, okay, table on the left, the specification of the custom material is obtained from the research paper Zhu et al., as you can see right here. And then for mesh generation, after we have designed and we have assigned all of the materials accordingly, then we can perform the mesh generation after we import the 3D models into the software. So the meshing process is done by utilizing access mechanical, and then it is crucial to determine which parts of the model need to be meshed and which parts do not. For example, the design of the lunar rover has been simplified, okay, by discarding the bolts, the nuts, the screws, and also the metal chains. Because if we increase the parts, okay, the useless parts, okay, in other words, the number of elements in it will increase, hence the software will consume a large amount of time to generate the mesh. So we try our best to identify which parts that will not use, and then we just concentrate with the parts that is crucial. So these are the mesh generated by each models by the software. The mesh generated is a hybrid mesh structure. Okay, the ideal structure mesh is very difficult to achieve as the design is relatively complex and complicated. So the mesh generated is befitting by taking into account the design complexity and computer hardware capability. And then we have to perform mesh dependency check. Okay, because the result becomes more accurate when the mesh is a model is final, and the computation time is greater as the mesh is made final. So the main objective for mesh dependency check is to obtain a mesh that balances satisfactorily the computing resources and accuracy. In this study, there are 4 numbers of elements will be used for mesh dependency check. These numbers include according to the slide that I showed. So this is the mesh dependency check for a lunar rover with a conventional wheel loaded with a 500 Newton load. The number of elements for the third solution number, which is 213076, can be a modest option. Okay, element number to perform static load simulation of a lunar rover with conventional wheels, considering the computation time and result precision. During mesh dependency check, I encountered some problems, and these problems are the software unable to generate a final mesh for simulations in validation process and simulation for lunar rover with flexible metal design, because this is due to the limited computation resources as the solver having insufficient memory to solve the solution, to get the solution, and unspecified specification of some parts of the flexible material design, like the thickness and width of the connecting rim and the rim, are not stated in the research paper. So the solution to my problem is the simulations will be carried on conducted, but by using the default mesh generated by the software. So boundary conditions, these are the boundary conditions, okay, for validation process simulations, and also the statistical simulation for lunar rover with conventional wheel, and statistical simulation for lunar rover with flexible metal wheel. So next we take a look at the result and discussion. So validation process, as you can see, most of the results in validation process is tally with the research paper. As you can see at the percentage error, there are only 10 to 15% percentage error, meaning the design is valid for to be used in statistical simulation of lunar rover later on. So this is the results of finite element analysis of lunar rover with conventional wheel. So the finite element analysis of lunar rover with flexible metal wheel, and these are the comparison of lunar rover with conventional wheel and lunar rover with flexible metal wheel. As you can see, the mechanical properties of the flexible metal wheel is slightly higher than the conventional wheel. Okay, 7 to 8% for the maximum deformation, 11 to 15% to von Mises stress, maximum von Mises stress, and 30%. Okay, for the strain, the mechanical properties of lunar rover with flexible metal wheel is moderately higher, okay, than other mechanical properties. And for the total strain energy, the maximum percentage difference is only 6.46%. So these are the comparison of lunar rover with conventional wheel and lunar rover with flexible metal wheel. So these are the location of maximum stress. Okay, on the left hand side is the location of maximum stress at the if the lunar rover implemented with conventional wheel. As you can see, the maximum location is located at the critical component of the lunar rover, which is the drive shaft. As you can see on the right hand side, the maximum location of the maximum stress is located at the flexible metal wheel. Next, the location of the maximum strain is located also at the drive shaft, at the critical component of the lunar rover, while the maximum strain, on the other hand, when the lunar rover implemented with flexible metal wheel, is located at the body of the lunar rover, or frame of the lunar rover. So these are the ISO lines for you to clearly observe the differences between the application of conventional wheel and flexible metal wheel. So, and then conclusion. Okay, the mechanical performance between the lunar rover implemented with a conventional wheel and lunar rover implemented with flexible metal wheel are considerably similar, with the minor percentage differences only, as you can see on the table that I provided earlier. However, flexible metal wheel design, or the improved design, helps to evade the majority of the stress and strain distribution from concentrating at the critical components of the lunar rover, like motor case, the drive shaft, and frame. Furthermore, the wheel could act like a suspension that absorbs the energy, allowing the body of the lunar rover to traverse undisturbed along the uneven surface. Also, the improved design offers a higher strain energy, okay, meaning to say that the lunar rover can recover much quicker when it is loaded with an immense amount of load, okay, compared to the conventional wheel. So therefore, we can conclude that The improved design has been proven to be a better way by conducting FEA simulation, as it provides a better design in impact absorption, especially on complex terrain of the lunar rover. So I guess that is all from me, and thank you for listening to my presentation. Assalamualaikum.